Question 7, back to waves. We're talking about a sound wave, which is a longitudinal wave, and hence we have compressions and refractions. Now we're asked to explain the terms compression and refraction, but be careful here with the instructions because it's quite picky about what it wants. But it does say it. So it says, give your explanation in terms of the spacing of the molecules. So for each of these, we want to talk about the spacing of the molecules, and we want to talk about the pressure. So for each of these points, I need to talk about both of these things. So with regards to the spacing of the molecules in a compression, the molecules are close together. And with the refraction, my molecules are farther apart. But that's not enough, because my question is also asking me to talk about the pressure. So I'm going to go back to each of these. Compression, if my molecules are close together, that means it's an area of high pressure. And in my refraction, because my molecules are further apart, it's an area of low pressure. So again, make sure you're talking about both of the points that the question is asking you for in both of the answers. Then we have a calculation. So we have an instrument with this given frequency. Now careful here, note that this is in kilohertz. So we're just going to make a note for ourselves that this is actually 4,400 hertz. We are given the speed. And now we want to calculate the wavelength. So frequency, speed, and wavelength. We know that equation. It's the universal wave equation. Speed is wavelength times frequency. I know my speed. Wrong number. I don't know my wavelength, but I do know my frequency. And then, divide both sides. And then I end up with a wavelength of 7.7 centimeters or 0.07 meters, which I prefer. Meters are definitely the unit to go with when in doubt. And then we have this same instrument. Initially, it was at 4.4 kilohertz. Now it's at 5.1 kilohertz, so that means that our frequency increased. If the frequency increased, that means it's now playing a higher pitch. And the amplitude of the sound increased, so that means it is louder. These are just notes I'm making for myself as I'm reading the question. I don't actually know the question yet, but this is just what happened. You need to understand what happened. Now, without calculation, state what happens to the speed of sound. So based on the notes that I just made, I changed pitch and I changed amplitude, but neither one of these two things affects the speed of sound. Speed of sound only changes if I change medium or if I change temperature. And neither of those two things have happened. I'm using the same instrument in the same environment. Nothing that would change my speed has actually come into place. So change of speed, no effect. Nothing's changed my speed. And wavelength, if I have changed my frequency, but my speed is the same, again, I'm going to just write my wave equation to keep track of that. My speed is constant, but my frequency has increased because I have a higher pitch, right? It went from 4.4 to 5.1 kilohertz. In order for my speed to stay constant, I need to balance this out, so my wavelength is going to have to get smaller, which makes sense. Usually a higher pitch sound has a smaller wavelength, and it comes from the fact that a higher frequency with the same speed needs a shorter wavelength.